Okay, welcome to Module 3 of the Everything You Wanted to Know About Data But Were Afraid to Ask. And we're going to dig in today to what I'm calling the archaeology of patterns. And I think the archaeology piece will become clear as we move along. Today, basically, what we're going to be looking at is ways to kind of visualize data that you're collecting, whether it's for an IEP goal or objective or some school-wide measure. The key thing is to be able to think about different ways in which you can look at data, both really the actual visualization of it in terms of different kinds of charts, but also just ways to think about what you're seeing and how to pull out patterns from what you're able to see with the ways in which you're both collecting it and showing it. Okay, so let's dig in here. So the first part I want to share with you today is to think about the notion of pattern is like you're excavating and getting information out. And so what I want you to think about is what do we see when we see certain kinds of things in the world, and what can we infer or conclude from what we see. So the analogy or metaphor I want to pick up on here, which is why it's called the archaeology of patterns, is I want to imagine that you're kind of an archaeologist, right? You're out on a dig and you're looking information and you pick stuff up and you've got your various tools. And maybe you find a skull, okay? And you're trying to understand what can be inferred from the skull. And so if you're someone who's well versed in our human evolutionary history, our hominid evolution, you might look at a skull like this and see, okay, I've got this distinctive brow ridge, and what I know as a kind of an archaeologist interested in human evolution is that when I had that distinctive brow ridge, that looks something like our earliest ancestors, some of the chimpanzees or apes, right? I've got these large cheekbones and this set-in kind of eyes, and then there's a flattening of the nose area, and that tells me something that's fairly ancient. Okay, so from the patterns I see of the skull, I can draw inferences or conclusions about what type of species this might have been. Other kinds of patterns, and this is a classic image from way back, so almost 4 million years ago, of one of the first hominids who walked the earth, and one of our earliest ancestors, is that this clearly showed, because of the footprints, that they were walking upright. Okay, and so that's a change in our evolutionary history from the chimpanzees and gorillas who were kind of walking on their knuckles. So from the data, in this case, these certain structures, right, the skull and the footprints, I can draw some conclusions or inferences about what was going on. Okay, so I want you to think of yourselves as archaeologists excavating patterns, in your case as educators, whether you're a teacher or a clinician or a therapist, school psychologist, you will be collecting certain kinds of data or evidence to help shape what you're doing with children. So you might get a pattern that looks like this, where you've got something going along perhaps on the x-axis or horizontal axis, which is, let's say, time or date, and then some measure of the skill of this individual based on your assessments. And you might find that early on you did a whole bunch of assessments and there was oddly kind of like a bunch of different distributions of data, and over time things spread out and they begin to change, and you get this very kind of linear pattern of change over time. But then towards the end, boom, a little outlier here where all of a sudden the skill or ability or whatever it is pops up. So we're trying to look at the distribution of the data in such a way that we can make inference about what's going on. Has the child grown? Is there stagnation? What's going on in the patterns that can tell us what we might do to help shape further growth or change? So the first thing I want to speak to is the notion of distribution. And this is really about how you can visualize the sample of data you have. So let's say you're taking data on paper and pencil. That information is going to appear in your check sheets, but ultimately you're going to want to plot it in some way that allows you to see potential patterns, right? Or you might have an Excel sheet or a Google sheet, and from that you can create a chart. Or you may have other kinds of software that automatically plots your data for you. But whatever systems you're using, you want to have some way that you can actually see what's going on in your data. Okay, so here's an example, and you've got, again, typical plot, right, where you've got something along the x-axis or horizontal and something along the y. In this case, what you have here is potentially different groups, right, or different months maybe, right, where you have the dots being the samples you're taking, okay, so the blues and the oranges, and might imagine these being groups or month, September, October, November, and December on some measure. And what it's basically showing you is you've got a distribution in these different samples, either as groups or as months, okay? And the dark line you can see here on, let's say, the blue one, or the dark line cut across the orange or the purple might be the average or the mean. And then the little boxes around that might be the kind of core concentration of your information with some kind of deviation. Okay. Here's something else that makes it maybe a little more concrete. Is imagine we've got date going along the horizontal axis or x-axis and some measure of skill, right, from low to high. Okay, so over time we're getting a pattern here where there's little change in the first 3 samples, and then all of a sudden things pick up again, seemingly, in this 4th sample, but then drop again in the next 3, then pick up again, and it seems like we're going up and up and up, and then all of a sudden there's this big drop down here, and then it comes back up and levels off. The reason why I'm kind of highlighting the difference between the blues and the oranges is that these indicate some kind of change from the pattern that preceded it. So again, we start off with very little change, and then there's a big change, it seems like, in the skill, and then it drops back down almost to the level it was before, and then pops back up, and now we're looking like we're on a growth towards improvement, but then it drops before it recovers evenly again in the last 2 samples. So what we would like to try to understand, and the reason why the visualization is so helpful in this case, is, well, what caused this drop? What happened on this day? Was the child distracted? Did they have a hard night before? Maybe it was a differences in how staff were assessing things or the composition of the classroom. But whatever is going on, the visualization draws our attention to see what's going on with the evidence we have. So that's kind of seeing the distribution. And again, what I want to remind people of here is that if we're only recording our data on paper, we somehow need to get that information into some kind of graphic, right, so that we can see that distribution. And that's why, certainly nowadays, getting information quickly into a digitized system so that we can take advantage of charting opportunities will ultimately help us be more efficient in having the time to look at our data. Okay, so that's a little about distribution, and now what I want to share with you is that, of course, there's different ways of looking at your data, right? And different types of charts will help you see things in different ways, right? And depending on, again, the kind of program you're using, a digital program, you might find there are different opportunities to take the same data set and visualize it in a different way, and that can be very useful because, as you will soon see, different types of charts show things in different ways that can really help you understand what's going on with a child or a group of children. So pie charts can be very helpful, especially when you have categorical scales, something like poor, fair, good, or excellent, or never, rarely, sometimes, often, always, right? Where you're looking, let's say, at the proportion of entries for each part of the category, right? Or the number of records, right? So in this little graphic up here, right, we've got kind of 3 components to the pie chart. Let's say it's, rarely, sometimes, and often, right? And let's say the biggest part of the pie chart, maybe about, we've got here, right, something, like almost, 67%, let's say, or more, 75% actually in this pie chart. 75% of the data is in the rarely category, and then an equal amount in the sometimes and often. Okay, so that gives you kind of a snapshot of where that child is, and that's very helpful for seeing the proportions of things, right? Okay, but that's a static representation. There's no time information in that pie chart, so that's one of the limitations. If we want time varying information, then we want maybe perhaps a line chart where, we might have over time, the horizontal axis is basically date, let's say, or it could be time within a day. And then the y-axis, where the line is varying, is some level of skill or performance measure. Okay, so line charts can be very effective at showing what's happening over time. Scatter plots, in contrast, can show kind of the distribution of scores. So let's say I've got a quiz, right, where the scores can go from 0 to 50, and I'm giving you bins here in fives, right? So a score of 0 or 5 or 10 or 15 all the way up to 50, and each dot represents a score by a student, let's say in the class or the grade. Okay, so here I can see the distribution of scores as a function of 5 point differences within my quiz, which sums to 50. Okay, so I can see here that there are fewer students getting in the 45 to 50 range, quite a few from 40 to 20, and then again a few who are in the lower end of the distribution. So again, this can give me a sense of whether I've got something like a normal distribution perhaps, or something that's skewed towards one end or somewhere in the middle of the distribution of scores. And then lastly, bar charts can be very helpful for comparing groups. Those could be ages or grades or months, or it could be, if you have a population within special education of different types of disabilities, what's going on average with those different kinds of disabilities. So in a bar chart, what we might often be representing are averages with some kind of grouping factor. Okay, so the key point here is that we want to be thinking about whatever kind of data we have, what are we trying to understand about the data, right? If we want something like an overall percentage of different components of a scale, like a categorical scale, that might be best shown with a pie chart. If we're trying to see whether things are changing over time, then we might want to look at a line chart. If we're trying to see the distribution, let's say in a grade or something like that, where we want to see how many individuals get certain kinds of assessments, then we might want a scatter plot. And if we're looking for grouping effects by age or grade or months, then we may want to look at a bar chart. Okay, so now we've gone from distribution and visualization to now some of the more statistical properties. And here I want to really flag some of the issues that come up when we talk about IEP objectives and benchmarks in particular. It's often the case that in the objective and benchmark section, people are reporting out on a particular statistic, like so-and-so will have an average percentage, let's say, of 80% or greater. What's often not considered, but I think is absolutely critical to understanding what's going on with children, is understanding the variation. That whenever we report out on something like an average, that is based on a number of samples which may have variability. And part of the goal is to understand what can cause the variability. So this little kind of cartoon image here, again, shows a distribution of dots, the gray dots, and then the black line is kind of the average of those dots. And then the next little image here shows kind of the standard deviation or the variation plus or minus around that mean. And then over here to the gray kind of abstracts away from all the dots just to show the ranges, perhaps, the minimums and maximums of those scores. Okay, so again, going back to that notion of distribution, it's very important that we understand the variability around what might be considered an average or a mean. Okay, what that plays into is that when we're reporting out on an average, it's important to consider the sample size we have that we think perhaps represents that average. And here is where I want to appeal to what's often called kind of the law of large numbers or the law of small numbers to show what that can do to our understanding of that report of an average. So let's say we're, just to kind of give an analogy here, let's say we're looking at somebody's free throw record in basketball, right? So they're, what are the odds that this individual will hit, the free throw? And, let's say we've got a sample for LeBron James, who's, obviously played a lot of basketball in his life, of some thousands of free throws. So we have a huge sample size. If we say on average, LeBron James hits 80% of his free throws, well, based on thousands of records, that's likely to give us a pretty accurate sense of his probability of hitting, a free throw. The contrast is if we've got a brand new player, right, who has never been in the books, right, in the NBA, let's say, and we have no prior history, well, if we've only seen the first game where maybe he only had 3 free throws, our ability to predict how well he will do is just that much less, because he could have had a great game or he could have a really bad game, and we're not going to be able to predict. Okay, so that's the kind of different way of thinking of large and small, and I want to just illustrate that with a coin flip to just show you how one could be potentially misled by small numbers. And that's why it's important to get a sufficient number of assessments to say that the average is representative of whatever you're measuring for a child. Okay, so here's kind of the idea. Let's say we plot along the, again, x-axis or horizontal axis, the number of coin flips. So I flip it once, I flip it twice, I flip it 3 times, right? And then along the y or horizontal, vertical axis, the cumulative proportion of heads. Okay, so I flip it, and what do I get? And so now I'm going to see what proportion are heads or tails. So imagine we have a distribution like this, right? The first flip is a tail. So obviously the proportion of heads is 0. I flip it again, and it comes up tails again. I flip it 5 times, and each time I flip, or 4 times, each time I flip it, I only get a tail. So the proportion of heads is 0. Does that mean that the probability of getting a heads is 0? No, it just means that on the first 4 flips, that's what I got. The next flip, right, on the 5th flip, I get a heads, and now the proportion would be 20% because I have 1 out of 5 flips. And on I go. By the time I get to the 10th flip, I've had 5 heads and 5 tails, so the proportion of heads and tails is 50%. As I presume you know, the odds of getting a head or a tail is exactly 50-50 as long as it's not a biased coin. That's important because it's what's often called the gambler's fallacy, right? Let's say you flipped it 4 times and you got tails, and now your friend says, oh man, you're due, man, you're going to get a heads this time. No, the probability of a heads or tails is always 50-50, again, assuming it's not a biased coin. Okay? But it just shows that if you only have small numbers, right, you might be misled into thinking, oh, well, the probability is 0 of getting heads because I keep getting tails. Okay. So to sum up, you want to make sure you have a sufficient number of samples to give you an accurate representation of the average, right? Small numbers can greatly throw that average off. Okay, so this then brings us back to another way of thinking about variability, and here I really want to stress how important it is to plot your data, as we talked about at the beginning of this module, so you can see the range of variability in a measure. Now let's take this here, right? And let's say, we've got some measure that goes on over, days, let's say, and here's the score, and let's say some kind of ELA, right? Okay, well, we can quickly see here that we've got kind of minimum and maximum scores, right? So here's a minimum score down here near 55, and here's a maximum score here up, maybe around 77, okay? So that's the minimum maximum. Now, clearly, if we were to draw kind of a line indicating kind of what's happening over time, we'd have kind of an increasing pattern, right? Okay. Now, even though that's true, what we can also see is that even here by the end, we've got a distribution of scores, right? If it's a student, let's say, this student, even on this last day, can do pretty poorly, but it also can do very well. We also can see that there's a kind of a range, a tight range of variation that the score stays the same from the beginning and all the way to the end. So what we need to understand in a distribution like this is what's driving it. Okay, so we've got scores that are low at the beginning and we've got scores that are low at the end. Why? But we also have an overall improvement over time, so we get more and more high scores towards the end. So something good is happening. Let's say if it's a score on an ELA quiz or a math quiz or something like that, right? The student is doing better and better, but still is capable of some pretty poor performance. And so our job as educators, and again, it doesn't matter if this is a clinical assessment or a therapeutic assessment on speech or physical therapy or an academic assessment. What does the distribution tell us? Why is there variation? How can we understand that? Because the more we can understand those differences, be they within an individual or between individuals, the better we can streamline and make optimal the kinds of teaching we do to help growth, and in many cases to reduce that variability, right? Okay, because let's say this is a performance measure, how we can do with skills, right? We want to capture what it is that helps the child do so well up here, and we equally want to understand what's making them do so poorly down at the bottom. Okay? So that's about variation. I want to now turn to the use of percentages, because again, this is a very common type of scale, basically, of measurement. Obviously, it appears many, many times in academic areas where you're scoring the percentage correct, let's say, or accuracy in physical target grasping or accuracy of speech enunciation, right? So percentages are very common. And what I want to talk about today is the basis that goes into percentages to help you think about some of the ways in which you can get caught up and give inaccurate percentages sometimes, so that you can give the best kind of accuracy when it comes to using percentages. So percentages are useful often when you have something like, let's say, just using a concrete example, a daily schedule, right? So I'm going to do 12 things each day, and I'm going to score the child in terms of their success in each of those. They either did it or they didn't do it, let's say. So, they arrive at school and they get settled into their routine. They check in, okay, they did that or they didn't do it. They did their reading or they didn't do it, and so forth and so on, right? They get on the bus properly. Okay, so I have 12 events that I'm going to score as did it or didn't do it, right? And let's say that, this child finishes his day and today he does 6 out of 12 well. Okay, so 6 out of 12, 50%. Okay, so each day I indicate whether he does it correctly or incorrectly out of 12. But as many of you know, some days are half days. Some days a student may arrive late and not get there until reading, or may leave early due to a doctor's appointment and therefore leave, let's say, at art. So all we've got is 9 sort of scores, right? So 1 through 9. If we were simply to tally up the number of did it correctly or didn't do it correctly, we would get different numbers, but we wouldn't be able to think carefully about short days versus full days. Okay, so just to give you an example, like the first one, a full day, the child does 6 out of 12 correctly, right? Let's say he does the first 3 correctly and he does the last 3 correctly. Okay, 6 out of 12 correctly, 50%. The next day, the child leaves after recess at 6, so only gets the first 6, right? And here he does 3 out of 6, also 50%. But that's very different. On one day, he completed all and got 50%. On this day, he was there for only 6 and therefore completed the same 50%. So when our numbers vary, percentages can be very useful as opposed to raw scores. The same thing, of course, is true if we're doing something like duration, right? If we want to look, let's say, at the amount of time a child is non-compliant. Okay, so we are timing the number of minutes. Okay, and let's say we've got a full day of school, which is 6 hours. 6 hours times 60 minutes, 360 minutes. So we might be entering the total duration of time that child is non-compliant. And so on one day, we enter, let's say, 60 minutes. Okay, 60 minutes the child was non-compliant over the course of a full day. And we're entering 60 minutes one day, 60 minutes another day, 70 minutes, 80 minutes, and so forth. The problem with just recording duration is that, again, if the day length varies, 60 minutes out of 360 is very different than 60 minutes out of 60 minutes. A child who's 60 minutes out of 360 non-compliant is only 1/6 of the time non-compliant. A child who's non-compliant 60 minutes out of 60 minutes is non-compliant the entire time. Okay? So percentages will give us a more accurate sense of what's going on when time or the number of events that we can process in a given day varies. The second thing that I want to point to is that when we are calculating percentages, it's important that the number of elements that we're scoring stay within a comparable range. Okay, so to give you an illustration of that, let's say I'm doing something like recognizing the letters of the alphabet, right? And so I'm looking at uppercase and lowercase, and what I hope to achieve within a given session or opportunity is that we get through all 26 uppercase letters and all 26 lowercase letters for a total of 52 effectively trials, right? Where I'm saying, okay, here's capital A, what is it? Child says capital A, then I go to lowercase g, and so forth. Okay? Now, as is always the case in schools, we have a plan to get through all 52, but things happen and we may not get through all 52. So let's say some days we get through no more than 10, and other days we get through all 52. The problem with using a percentage in that case is that that variability is going to make it very difficult to interpret, right? So let's say I get through only 10 and I get them perfect, 10 out of 10. Another day I get through 52 and I only get through 10. Okay, well the percentages are wildly different, but in the first case, maybe I'm bright and alert in the first 10 trials, and by the end I kind of run out of steam. That's not an indication of my overall capacity. It's an indication of how alert I am, okay? So we want to bracket those numbers so that we say, I'm only going to accept, for example, a session if I can get through at least 45 to 52 of the letters of the alphabet. Other than that, I can't include it in my overall percentage score because the range of variability is too great and too many things may interfere with my understanding. Okay, let me show you another way in which different types of numbers can kind of hurt your interpretation of a percentage. Let's say we're doing something having to do with a quiz, and on our quizzes we typically give 3 questions, and we're then going to convert those quiz scores to a grade. Okay, so I have a quiz, and on one day the child gets 0 out of 3, so 0%. On another day the child gets 1 out of 3, or 33%. Then she gets 2 out of 3, or 67%, and then finally gets 3 out of 3, 100%. If I convert those to grades, right, on a standard kind of distribution of grades, the first 2 scores give the child an F. The second gives them maybe barely a C, or maybe closer to a D, and only the last score gets an F. So if I average, I've got an F, a C, and an A, and that's going to put that child close to the C or D range. Okay, so we get these skewed assignments if our numbers are very small when we make conversions to things like letter grades. So again, we need to be careful of those small numbers because they may not accurately represent what's going on with a child. And when we convert to something like a letter grade, we can really be off if we're then sort of going on the letter grade basis as opposed to the pure number. The last piece that I want to speak to, again, where the distribution issues can be very important, and this is going to link us to how to use data to understand what's going on with patterns of variation. And this brings up the topic of correlations and causation. So one of the ways in which correlational data can be very, very helpful, and this is maybe particularly the case in special education, where often there are a variety of things being assessed for a given child, is that we can look and see whether there's any kind of relationship between different measures. So let's imagine the following. Let's imagine we've got data on a child where we're measuring the proportion of, let's say, 15-minute intervals where there's aggression in blue, the frequency of non-compliance in a given day in red, and then the proportion of 15-minute interval bouts where we either do or don't see a tantrum. Okay, so the first two measures, aggression and tantruming, would be kind of interval sampling, where every 15 minutes either there is aggression or tantrum or there isn't, and then we're calculating the percentage of bouts or intervals with those behaviors. And then non-compliance is simply the frequency of non-compliant events we see in a day. And then here what you see are just days, of sampling, and then the scale here on the left-hand side. So, of course, for a percentage, it'll be 0 to 100, whereas frequency is just the number of events we're seeing. Okay. Well, overall, what we can see here is that on many days, when the aggression and tantrums and non-compliances are high, they all are, right? And when they tend to go lower, they tend to drop together. So there's a lot of days in which when one's high, so are the other two, and vice versa. But that's clearly not always the case. So if we look over here, we see that non-compliance and tantruming are rather low, but the bouts with aggression are high. And again here as well. So distributions like this can help us see when certain kinds of measures may be correlated, right? They move up and down together, and when that correlation may fall apart, allowing us to understand, well, what is going on the days when things are moving up and down together, and what's going on days where they come apart. Okay? So again, visualizing day-to-day variation among many different kinds of measures can be helpful in terms of orienting to us to those kinds of relationships. Okay, so that's about relationships or correlations between measures. But we must be very careful not to assume that because things are moving up and down together that one thing is causing the other. And that's a very important thing to keep in mind, because we wouldn't want to assume, for example, that, look, when a child is non-compliant saying no, they get so frustrated that that automatically goes into aggression and tantruming. I mean, it may be the case, right, that when a child's non-compliant and frustrating, the next thing is they escalate to aggression and tantrums. We don't want to assume the causal arrow between one and the other. And that's kind of nicely illustrated in this little cartoon here, right? Here's this, TV remote right through the TV, and the child, the mom's saying, why'd you do this? And the child says, correlation does not imply causation, right? Just because I'm standing next to the TV doesn't mean I did it. Okay. That's kind of nicely illustrated here, with two measures of, changes in ice cream sales and shark attacks. And of course, as you can see, as we increase into the summer months here, right, May, July, August, and so forth, these two things are going together, right? When it's the winter, we see very low shark attacks and ice cream sales, and when it gets hot in summer, we see high. Do we want to infer that, people are eating more ice cream when shark attacks are high? No, it just turns out in the summer months the sharks are around because it's hot and there's a lot of prey around for them to eat. And when it's hot, we tend to eat ice cream, right? These things are correlated, but they're not causally related at all. So let me sum up today sort of the archaeology, right, of patterns. We've said a couple of things that I hope are important and helpful for you. The first is that we really want to be able to look for patterns in our data. And so even if we're just collecting things on paper and pencil or putting them into a spreadsheet, we need a way to visualize things so we can see the distribution of our data and try to figure out what's going on. The second is that by visualizing it, we can discover patterns, right? And some of the potential causes of patterns, right? So minimum and maximum, or no change, or change over time, right? What's going on with that pattern of distribution? Third, we want to look out for small samples, because with small samples, they may not be indicative of things like our averages or of converting percentages into letter grades. So small samples can basically be deceptive in that they may not capture what's actually going on with a student who may be showing lots of variation, good days, bad days, times of days, and so forth. And then lastly, although it's very helpful to look at the relationship between different measures, do they come up and down together or not, we must be careful to not infer that one thing is causing another. To get at causality often requires doing things like specific interventions, where we design almost like a little experiment, right, to say, well, if I change out the staff, who's been typically working with this child, will that change the pattern of behavior which I thought when one staff is working with somebody, we get one pattern, and when another staff is working with that child, something different's happening. That's a correlation. If I change up the staff, I might be able to get more at the causation. So I hope today's discussion was helpful in terms of the archaeology of patterns, and I look forward to seeing you in the next module.